What is a geostatistical model? What techniques are needed to be able to fit disease transmission models to spatial epidemiological data? How can these methods help us understand infectious disease transmission dynamics in low and lower middle income countries?
We explore these questions and more in this episode of SPIDER Presents.
This is SBIDER Presents, a series produced by the SBIDER Podcast Hub. My name is Laura Guzman.
And mine is Ed Hill. To discuss these topics, today we welcome Dr. Simon Spencer, a reader in statistics and a member of the Zealand Institute at the University of Warwick.
Simon has research interest in Bayesian inference, fitting models to data, and model comparison, with applications to epidemiology, outbreak detection, and stochastic epidemic models.
In this episode, we will be discussing the research article Integrating Geostatistical Maps and Infectious Disease Transmission Models Using Adaptive Multiple Importance Sampling. The article is published in the Annals of Applied Statistics in 2021. Hi Simon, thank you very much for joining us.
Hi, lovely to be here.
Welcome to SBIDER Presents.
Thanks.
Would you like to share with the audience how you gain a general interest in statistics and the research area of fitting models to data?
Yeah, sure. So I swore that I would never become a statistician, but I did a PhD in infectious disease models, and I learned lots about different ways of modeling infectious diseases, but there's no data in my PhD at all. It wasn't a statistics PhD. It was more sort of looking at probability models. And when I finished my PhD, I really wanted to go and live in New Zealand. And my PhD supervisor knew someone over there who wanted to employ a statistician. And since I had a PhD in probability and statistics, I said, I'm a statistician. I'll come over and work with you in New Zealand. So I had a lovely time in New Zealand. But as well as enjoying traveling around New Zealand, I did learn some statistics. And the more I learned, the more interested I got. And suddenly I accidentally became a statistician.
That's awesome to hear. And so you might have already touched upon this. So the paper we'll be discussing in more detail is an example application within epidemiology and infectious disease modelling. Was this always a planned application that you wanted to undertake in your research, or was it an unexpected avenue?
Again, there was perhaps a bit of a happy accident in that I was at a conference in the poster session with a glass of wine in my hand and full of confidence. And I met someone at the conference who was interested in neglected tropical diseases, Professor Deirdre Hollingsworth, and she said to me, would you be interested in helping out this project I've got planned, looking at spatial models for neglected tropical diseases? And I said, yeah, sure, I can do this, whatever, it will be great.
That is a great story. Thank you for sharing. For this particular study, what were the knowledge gaps at the time? And what, therefore, were the specific aims of this study?
Yeah, so we'd written a previous paper already where we took just geostatistical maps and we tried to use them with transmission models to make projections into the future for disease prevalence in the future. But the method we were using required a tremendous amount of simulations from the model, and it was taking a long time to fit the models to the geostatistical maps. So in this paper, we tried to come up with a more efficient way of doing this, basically by using the results from the beginning to choose the simulations to do next so that it would be much more efficient and we wouldn't need to just do big batches of simulations. We could use the early stage results to target the next batch of simulations to the areas that we really needed more simulations in.
That's super helpful insights. And so within this study, were there particular data sets that were available to you, and were there particular strengths or limitations with that? And did that necessitate there being novel methods to be developed to be able to analyse them?
Yeah, so one of the really nice things about neglected tropical diseases is that all the data is publicly available on the SPEN website, the Expanded Special Project in Neglected Tropical Diseases. So all the data that's available is available publicly, and all we had to do was download it in terms of both the surveys and what interventions had been applied in different places across Africa. The downside was that for a lot of these diseases, the most cost-efficient way of intervening and controlling them is to not worry about who's infected, but just to turn up with a drug treatment and give the treatment to everybody, and then everyone who is infected with worms, for example, gets them removed from the system and they're better. And it's actually, more laborious to test everyone and work out who's infected and only treat the people who are infected than it is just to turn up and give everyone the treatment. This means that there isn't a lot of test data available. All the data comes from specific surveys where they've been trying to work out what the prevalence is. But a lot of the time they don't collect any data. They're just doing the treatments.
What are the key findings from the study? Were there any that were surprising to you?
I mean, the main sort of statistical finding of the paper was that we managed to use this AMIS algorithm, the adaptive multiple importance sampling algorithm, to target the simulations more precisely to the locations where we required more simulations. But the real surprise, I guess, was that, the AMIS algorithm is in a previous paper, but they, in the previous uses, they'd only looked at one target at a time. And what we managed to do was to look at every location in Africa all at the same time and to target all of them together, which had not been done before. So I guess the surprise was that it worked.
That's always quite a happy story to be able to tell.
It doesn't usually happen, but on this occasion it did work as planned.
With this method, which is able to work on this kind of continental scale, like one of the major implications of the study, were there any other main implications of your findings, and are there any notable limitations that the listener should kind of bear in mind with regards to the work, and which may also give directions for where future studies might be taken?
Yeah, so we're doing a lot of follow-on work using the methods in this paper to fit 5 or even more neglected tropical disease models to geostatistical maps and make projections forward in time. With this approach, it's easy when new data arrives to incorporate that into the model as well and to build on latest projections, taking into account the latest data. But there are several weaknesses with what we did. The main one, I think, is that actually when you look at the results of a geostatistical map, what you've actually got is a surface. So the correlation between different locations is captured in the samples that we get from the geostatistical map. And when we do the projections, we lose this. We only look at the marginal distribution of prevalence for each location further on in time. And we've lost all of the correlation between different locations. So getting data in the future and comparing it to our projections doesn't necessarily help you say what's happening in nearby locations when it does with the geostatistical mapping. I have some far-fetched ideas about how we might be able to bring this back in at a later stage, but we've not had time to get into that yet.
So related to the last comment on looking ahead, what in your view are going to be the pivotal challenges to address with respect to approaches for model fitting and model comparison and their applications to disease transmission models?
That's a big question. There's a tremendous amount that we could do better. We make a lot of simplifying assumptions in the modeling. We could take into account more covariate data about the different locations and the different populations, as well as losing the correlation. There are many individual small details that we could do better. We look at having a constant population across time when in reality it's growing and perhaps changing in different ways in different places. The other big challenge, I think, is talking about which is the right spatial scale to do the modeling at. So if you look at big spatial areas, then you have aggregated your information across the area. And so your modeling is sort of, it might be broadly correct, but it's not very helpful for the individual locations that might be different from the average for a big region. But if you look at too small a scale, then you find that maybe stochasticity is dominating the transmission. The model will tell you that that location on its own is not enough to support the maintenance of the disease, and so it will just die out in simulations for a small population without any income from neighboring locations. So to find the sort of optimal spatial scale to do the modeling at, or to do a hybrid of modeling across different spatial scales all at the same time in a way that is coherent is a really big challenge that I'm not sure we've got close to doing in a coherent way.
As a follow-on to that, is this going to be a challenge that's like particularly noticeable within the neglected tropical disease realm and for low and low middle income countries?
It's quite an exciting time to be working on neglected tropical diseases at the minute, because over the last sort of 15 or 20 years, there's been a lot of effort by funders and donors to make progress on reducing the prevalence of many neglected tropical diseases. And the World Health Organization produced a set of targets for the roadmap to elimination by 2020, and then they've updated them for 2030. But at some point, the strategy needs to change, because to start with, the prevalence was so high that this mass drug administration was a very effective way of reducing the prevalence to low numbers. But when you only have a small number of cases, it starts to be a very inefficient way of controlling a disease, because, you're giving everyone drugs to treat just a handful of people. So how we change the strategy at this point of time is a really good, really interesting open question. And I think modeling is a good way of addressing it.
So thank you, Simon, for joining us today.
Yeah.
And for explaining this fantastic work.
Thank you very much.
Thank you, Simon. Brilliant to have your insights and to discuss the work, and wish you the best with your ongoing studies.
Thank you very much.
This is our news section, where we have a couple of updates on recent happenings in the research group.
Firstly, the Scientific Pandemic Influenza Group on Modelling, Operation Subgroup of SAGE, known as SPI-M-O, a group to which several SPIDER members made multiple contributions to understanding and predicting the COVID-19 pandemic during 2020-2022, has been awarded the Weldon Memorial Prize by the University of Oxford.
The Weldon Memorial Prize is awarded annually for noteworthy contributions to the development of mathematical or statistical methods applied to problems in biology. This year, it has been awarded to the SPI-M-O group in recognition for their work during the COVID-19 pandemic.
The awards committee said, under great pressure to deliver results quickly and under immense public scrutiny, SPI-M-O both built on existing science and developed new epidemiological and statistical techniques to understand the spread of the virus and how it might be controlled. The importance of good and timely disease modelling for policymakers has never been as clear.
Matt Killing and Louise Dyson were invited to attend and represent SBIDER at the Weldon Prize, given in Oxford on the 14th of November of 2022.
Our second piece of news is that the Tommy's charity launched a miscarriage support tool that uses a miscarriage model developed in Nigel Burrow's group. The support tool aims to give women with a history of miscarriage an estimate for the probability of successful pregnancy, and thus alleviate some of the worries associated with repeated pregnancy loss.
That wraps up our news section, and we wish you all well for the end of 2022. Thanks for listening to this episode, and we hope you will join us again next time.